All right, so we're still talking about matching here. And so the thing with matching is that there's a lot of decisions that have to be made in the process of going through the matching procedure, because our goal is to get a treated group and a control group that are comparable across all the variables that we want to match on. Every time we match on a variable and we pick a variable that we're going to make sure that this sample looks very similar to that sample on the terms of that variable, we are closing a backdoor. But how exactly do we do that? So let's walk through 5 decisions that we might have to make in terms of matching on a variable and see how those decisions play out. Now, we're only going to be using one single matching variable here, which is not typically how you would actually do a matching study. Typically, you'd be matching on more than one variable, but it's going to be a lot simpler to go through if we just use one. So let's use this particular example. So here I have data on 30,000 credit card holders in Taiwan in 2005. I have their monthly bills. I also have whether they repaid their credit card bill, looking at both their bill in April and also their bill in September. So what I'm interested in, I want to know the sort of stickiness of credit problems. So I want to look at whether being late on your payment in April is related to being late on your payment in September. Now, I might be worried about one particular backdoor, which is the size of your bill in April. If you have bigger bills in April, you're likely to also have bigger bills in September. And I'm really trying to isolate the sort of how late are you willing to be thing, and not just you're having difficulty paying back your bill. So big bills might make you more likely to be late in April and also more likely to be late in September because you're also likely to have bigger bills in September. So I want to match on how big your bill was in April. This is a continuous variable, right? What's my treatment here? My treatment is whether you were late with your bill in April. I'm looking at the outcome of whether you're also late on your bill in September. And I want to close the back door that goes through how the size of your bill in April. That's my matching variable. So I'm going to match on that one continuous variable. So here are 5 questions I need to answer in order to figure out how to match on this single variable. The first one is this: what is our matching criteria going to be? Now, the goal of what we're doing is to take our treated sample, people who were late on their bill in April, and create a group of people who were not late on their bill but are very similar to our treated group. But what does similar to actually mean? Well, I've got this variable that determines, how big your bill was, and I want people with similar bill sizes in April, but I can't just say make sure that the bill sizes are exactly the same, because then I wouldn't have any matches, right? If this person over here has a bill size that's, 37,432, how many people over here are going to have 47,432 as their exact bill size? Probably nobody. So if I insist that it's just they're the same, then I'm probably not going to be able to match on anybody at all. So if I'm talking about a continuous variable, I need to decide, what does it mean to be close, right? How close do we need to be exactly? What does it mean to be similar? Well, in the case of a single variable, that's usually kind of easy, because I can just say, well, how far is it apart? This person's 43,000, this person's 43 and 1, that's close. The difference between those two is 1. That's probably pretty close. And the bigger that difference is, the more different they are. So in the case of one variable, it's relatively easy. It's just what's the difference between this value and that value. And if I find somebody over here whose difference is very small with this person, then I would say that is a pretty good match. Things, of course, get more difficult once you add more matching variables, because if you have 2 matching variables, what if they're similar on one of the variables, but less similar on the other? How do you combine those two things? And we have to have a measure of distance. But thinking just about one variable, we can take this graph as an example. We're looking along the x-axis here. That's our matching variable that we want to be similar on. We have an observation here who was treated. That's observation number 10,305. That's their row number in the data. And if I want to pick a good comparison for them, I want to find somebody else who is very close to them on that x-axis, on that matching variable. So I got 2 candidates here. I got row number 27,719, which is a little bit lower in terms of their bill in April, and also 27,281. These are observations of people here, that's not the size of their bill. Now, all 3 of these observations had bills in April that were close to 91,600. And so we would say that these are pretty comparable. So if I wanted to pick a person to compare to for person 10,305, I would probably pick one of those people who are very close. And whoever is the closest might be the one who I would pick. Now that answers question 1. What does it mean to be far apart? It's just simply having a value of the matching variable that is similar. All right, so that brings us to question 2, which we already talked about a bit in the last video, which is, are we selecting a set of matches, or are we constructing a weighted matched sample using weights? These are 2 different alternatives. We could just pick the best match, or a certain number of best matches, and say, this is my set of control observations. They were the best matches that I could find. Or we could construct weights, where we give people bigger weight the closer they are to the thing I'm trying to match them to. So this graph shows two different ways of potentially doing this. So on the left, we see one-to-one matching. So I've got my one treated observation, again, lucky number row 10,305, and I want to pick the best match for that observation to be compared to. So that's whatever the closest observation is in the control group, which happens to be row number 27,281. That is simply the single control observation that is closest to my treated observation. So that's the best comparison. So that's the comparison that I'm going to use. I'm going to say that those two observations are basically the same, except one got treated and the other did not. You'll notice there's only one comparison observation. I could pick more. I could say what are the two best matches or what are the three best matches or whatever, but in each case, I'm just picking the best matches and discarding the rest entirely. They all get grayed out. On the other side, we have the option of using weights. Perhaps instead of just picking some to be in and some to be out, I will count the ones that are closest more. So notice here, the circles are the biggest circles are the ones that are closest to my 10,305 observation, right? The control observations with the bills in April that are most similar to that treated observation, those get the biggest weights, the biggest circles. As you move away from that closeness, as you get slightly farther and farther out, they count less and less. The circles get smaller and smaller. I'm simply counting them less. I'm giving them lower weights in the comparison group. Once you get to a certain distance away, you stop counting them entirely. Like, that's too far. That's not a good comparison at all. But the idea is the closest ones count a lot in their comparison. Those are the best comparisons. As we get further away, we count them less and less and less until we say they're too far away. We're not going to count them anymore. So we can either pick a set of best matches, or we can allow the quality of the match to degrade as you get further and further away, eventually dwindling away to nothing. So that's our second choice. Again, like I mentioned in the last video, there's a bias variance trade-off here. If we simply pick the best matches, like the one on the left, we are picking the best matches. So the bias is going to be lowest. We're going to do the best possible job of closing that back door. But we only have one observation in the control group there. That's going to be very noisy when we estimate what the control group's average is, so we can compare it to the treated group. Whereas on the right, with the weights, we are allowing some worse comparisons to creep in there. Maybe we're not doing quite as good a job of closing the back door, but we have more observations to take the average over, and therefore we're going to be more precise in our comparisons. That's the trade-off of bias versus variance. All right, that brings us to question number 3, which is if we are choosing to select a set of matches as opposed to using weights, how many matches are we going to pick? You could, like in that graph, only pick one match. But of course, doing so means that you are very much limiting the sample size of your control observations. But you could pick more. Like I said, you could pick the best 2 matches, the best 3 matches, the best 4 matches, the best 5 matches. You could do whatever you want. Now that said, the more matches we pick, there's a bias variance trade-off, right? As we go back into the well to pick the next best match, and then the next best match, and then the next best match, we are consecutively picking worse and worse matches. So we're inviting back in more bias the more matches we ask for. But we are also getting a bigger comparison group with more observations in it, which should make our estimate more precise. So bias variance trade-off, you only pick one single match and get a very good comparison, but it's very noisy in your estimate, or do you pick a lot of matches and so you get worse comparisons, but also you get a much more precise estimate of what the average of these comparison groups are. So that only applies if you're picking matches, but that is the trade-off we get. That brings us to question number 4. If we are using weights, we're assigning different weights to the control group, and then we're averaging them together using those weights. Well, how will the weights decay with distance? We know that as we get a really, really good match, we're going to weight you a lot, and as the match gets worse and worse and worse, we're going to weight you less and less and less. But how quickly does that go down, right? Does it go down very quickly, in which case we are basically only using the best matches, and getting a similar bias variance trade-off, right? We're only picking the best matches here. We scale down very quickly. So we're counting fewer observations, but we are getting the best comparisons. Or do we allow it to decay very slowly? We include a wide range of observations as comparisons, although with small weights. And so we get a much more precise estimate, but we're allowing in more bias. So the question of how quickly the weights decay or don't will sort of isolate that sort of bias variance trade-off question when you're deciding what to do about your matching procedure. But there's also the question of just literally what function are you going to use to describe the decay. You have to give it some sort of function so it knows what kind of decay to give it as you move further away. You know, does it look like this? Does it look like this? Right? Does it look like this? There's some function that's maximized at the center when you're as close to the treated observation as possible and gets smaller as you move away from it. There's a bunch of different kernels you could pick. Some popular ones might be the triangular kernel, which looks like this. There's the Epineshkinov kernel, which is a bit more curved. It sort of decays more slowly and then more quickly. There's a bunch of ones you can pick. They each have their own pros and cons. I'm not going to get into the technical details, but there is a question of exactly which kernel are you going to choose that describes what the decay of the weights looks like. So then finally we come to question number 5 that we have to figure out when we are doing a matched approach, which is what is the worst acceptable match? So let's say that we're trying to pick a set of matches for comparison. And we got this observation over here, and their bill in April was, let's say, 1,000, okay? And they were treated, they were late on their bill in April, and then we look at the control group and say, okay, let's find a match for you. And it turns out that nobody in the control group has a bill anywhere near 1,000. The closest best match, if we had to pick a single best match for them, is somebody who happened to have a bill in April that was like 6,000, way off. Now, the goal of doing this whole matching procedure is to construct a group over here that looks a lot like the group over here in terms of the matching variables. But now, even picking the best match we possibly have, that's still not a very good comparison, right? So we might say that that match, 6,000 to 1,000, is just too far away to really believe that we're getting a comparable control group. So we would say that that match is too bad to even count. So in that case, we'd take this 1,000 over here and just drop them from the whole sample. We'd say, we don't have a match for you. We're going to have to ignore you. We're going to have to drop you from the treated group. We're not going to find a match for you at all. So then the question is, what is that cutoff? What is the quality of match that gets so poor that you're not even willing to count it as a match anymore? Now, in the case of constructing a matched sample where you're just picking a certain number of control observations, there is the question of how far are you going to go? I mean, if you're taking only in the best match, well, again, is the best match within the range of that worst acceptable match, or is the best one outside? If you're picking more than one match, you have to ask, well, are there enough matches, right? Maybe there is one control observation that has like 1,100, and that's close enough. But then the next in line is 6,000, and that's too bad. So in that case, even if we were trying to pick, let's say, 3 matches for each treated observation, we would stop at 1, because anything other than that would be too bad. Now we get the same question on the weighted side. When we're applying these weights, the weights decay as we get worse and worse matches, but at some point, generally, the kernel goes to 0. We would say that the match is so far away from the treated observation that we're not just going to give it a low weight, we're going to give it a 0 weight. And then the question is, how far away is that, right? Are you going to go to 0 very quickly? Or are you going to go to 0 very slowly and accept some pretty bad matches? So in both cases, you have to ask yourself, what is the worst match that I would be willing to say is comparable at all? Or are the matches all so bad that I'm going to have to throw out a treated observation because there's simply no control observation that is like it? Now, this is, of course, a subjective question. You might ask yourself, well, can I really justify saying that these two observations are comparable when it's 1,000 to 6,000? Maybe not. And where's the cutoff for that? And of course, as with everything else, there's a bias variance trade-off. The worse matches you are willing to accept, well, you're going to have more observations that find a match, right? This 1,000 over here might have to get dropped if we're really strict about what a good match might be, and we're going to shrink our sample by dropping it. So that's going to make us less precise because we're going to have fewer observations to do our analysis on. But if we accept really bad matches, if we match that 1,000 to that 6,000, well, everyone gets to stay in the sample. We're going to get more precision in our estimate, but we're comparing some really incomparable things. We haven't really closed the back door there, so we're inviting some bias back in. So again, like with everything else, there is a bias variance trade-off in this decision. Going through these 5 questions tell us the kinds of decisions that we are going to have to make as we do our matching procedure. And this is going to be the case no matter what kind of matching procedure we do, at least in most cases. Some of the different kinds of procedures allow us to skip one of the questions or maybe even 2. But usually we're going to have to figure all of these things out. And that's what we're going to be doing as we go through the rest of this chapter. Thank you.